So I'm Noah. I am both a professor at Stanford and a fellow of the Uber AI Lab. Today, I'll be talking to you mostly from my Stanford point of view, because the Uber AI Lab has only been around for a month or two, and we don't have anything we're allowed to talk about yet. Um, so you guys probably know that at this point, at this particular moment in history, there's a lot of excitement about the fact that, oh my God, deep learning, computers can think. And to a certain extent, this is true. So these deep learning classification systems that are trying to do things like look at a picture and decide whether it's a cat or a boat have improved radically in the last 5 or 6 years. So this is the performance on the ImageNet data set. Back in 2010, it was nothing to write home about, especially compared to humans. As of last year, these systems are at or beating human level performance. So that's great, right? It's sort of great, but the problem with it is that classification is only a tiny little piece of intelligent behavior. And I want to basically talk to you about some things that I, from a kind of artificial intelligence and cognitive psychology side, see as super important ingredients that aren't incorporated enough in modern machine learning, but that we're working on. And I'll show you one or two examples. So in contrast to classification, humans think in a way that has a lot of properties, and three that I think are critical. Human thinking is abstract, and what I mean by that is that humans have knowledge that is used for many, many different tasks in many different domains. So you might have some implicit knowledge about physics that you can use for playing baseball, but also for moving things around the kitchen. You might have some knowledge about effectively chemistry that tells you what happens to a mushroom when you cut it and cook it. And that's useful for cooking. It's also useful in principle for chemistry and lots of other things. So having knowledge that you can use not just for one task, but for many tasks in many different situations is a key thing. Having knowledge that captures and deals gracefully with uncertainty is really critical. So in some sense, modern machine learning does this already very well, in the sense that if the input has a lot of noise and a lot of noisy features, you can still make pretty good guesses. On the other hand, there are kinds of uncertainty that humans deal with incredibly well that are much deeper, what we call latent randomness. So for instance, we have some knowledge about physics that lets us predict the trajectory. Imagine I'm holding a hammer and I throw it in the air, and you can imagine the trajectory. And you can do that even though you have noisy information. You don't actually have any idea where the hammer is. You're just sort of imagining, and incomplete knowledge. You don't know how heavy the hammer is, how it's balanced, and et cetera. And humans deal incredibly gracefully with this kind of uncertainty. Um, the final thing that I want to point out and talk about a little bit today is the social aspect of human thinking. So people not only are capable of reasoning about other people, we do it all the time. Even when it's not appropriate, we do it. So we're constantly thinking about why people did things. We're thinking, gosh, if somebody did this, what does it mean about how the world works? So we're learning from other people. In fact, if you imagine taking a person and raising them out of the context of other people, they're not good at anything. They actually can't do anything. So it's human culture and the ability to convey information from one human to another that's actually the critical piece of the success of our species. And that's not something that you see in pretty much any standard machine learning architectures. Your classifiers definitely don't do it. Okay. So let's talk about abstraction first. The good news, and I think a lot of you are software engineers, is that we already know how to represent abstract knowledge. Programming languages give us amazing tools for doing this. So programming languages give us a system for writing down kind of a uniformal representation of what you should do, what the computer should do, in ways that are abstract. You can write a function or an object and reuse it in lots of other programs to do lots of other tasks. Unfortunately, they don't have any of the other qualities that I'm interested in. They don't capture uncertainty in any useful way, and they certainly are not. Well, maybe they're social. Let's not talk about that. Okay. So programming languages are good for capturing abstraction. On the other hand, we have a set of tools, which are the tools of probability and statistics, which are great for describing uncertain knowledge and reasoning under uncertainty. The only problem with these tools is that it's really hard to represent the knowledge that you want to represent. It ends up being a kind of mishmash of math and English and other pieces. And that makes it hard to build systematic, complex pieces of uncertain knowledge that scale. So one of the potential sort of interesting ideas, I'm going to say that it's on the horizon, even though I've been working on it in some obscure corner of academia for a while, is probabilistic programs. Probabilistic programs are exactly the merger of all the best parts of programming languages and all the best parts of probability and statistics. And here's a very brief intro to what the idea is. Start with your favorite programming language. Here I'm starting with JavaScript. Add a primitive operator that does something random. It's basically rand, but we're going to do something better with it. So this is flip. It flips a coin, in this case with probability 0.3. You know what's going to happen if I run this program. I get some random answer like 2. The critical thing is to think about it in terms of what happens if I run this program over and over and over and build a histogram of the output. Okay, now what I have on the left is a little random program that you can think of as a simulator. What I have on the right is the probability distribution on outputs. When you build that histogram, you get a probability distribution. I could also describe that distribution this way using kind of mathematical notation. But there's a really interesting observation, it's actually a theorem, which is that you don't have to rewrite things in terms of the mathematical notation, that these two representations of uncertain knowledge are actually equivalent. So there's a theorem that says any computable probability distribution can be represented by a random program and vice versa. That's really cool because it means that if we want to build complex probabilistic models, we can do it by just programming and writing programs with proper abstraction and random choices in them. Okay, so we're halfway there. If all we could do was represent these probability distributions, which you can think of as simulators, we still couldn't do that much with them. We also want to be able to ask them questions, to interrogate them. And the way we do that is with conditional inference. So here's an operator called infer, and you should think of it as follows. You should think of it as first I give a model, there's A, B, and C again, and the thing I'm interested in, A plus B plus C. But then I get to make some assumptions or conditions. So here what I'm saying is, what's the sum of A plus B plus C, assuming that A plus B is equal to 1? Okay. Now, intuitively, what that means, you can think of it as a very similar kind of simulation process. Go ahead and run all the lines of code in that little infer block, except if the condition is false, cross it out and pretend it never happened. Okay, and then keep going and make a histogram at the end, and you get a different distribution. And this distribution is the conditional distribution, the answer to what's the sum of A plus B plus C, assuming that A plus B is equal to 1. This seems really simple, but it's actually the key idea that you need for first representing uncertain knowledge and then reasoning with it. We represent it with these random programs, and then we reason with it by simply doing these hypotheticals of enforce a certain condition on the execution trace and see what's left over. That's a lot like Sherlock Holmes, by the way. Here's the key interesting idea. We don't have to do it by that process of rejecting samples. We can implement inference in lots and lots of different ways, and there's a whole field of research exploring how we can define mathematically and then implement universal inference functions. So think about this as a compiler. You write an ordinary program, and you don't have to turn it into machine code because somebody else wrote a compiler. With a probabilistic program, you write a probabilistic program and the inference you're interested in, and you don't have to go write a hard statistical inference algorithm because that's somebody else's job. That's my job, actually. Yeah. Okay. I don't have a whole lot of time to talk about details here. But I encourage and invite you to go check out WebPeople, which is the language that I'm sort of showing you here. Somewhere there's an address there. If you go to webpeople.org, there's a code box you can play with and a bunch of examples you can fiddle with. And for those who are connoisseurs of probabilistic inference and such, I'll just mention that there's a pretty broad set of universal inference approaches in this system and in general in probabilistic programs. So whatever your favorite approach is, it's probably there, from dynamic programming up through crazy neural nets, which I'll say something again about in a few minutes. Okay, so now I want to show you hopefully 3 applications of this set of ideas. Realistically, 2 applications. So the first is, imagine what is Basically a toy domain, a toy model, tug of war. And imagine what is the set of concepts that you need in order to reason about tug of war, and particularly to answer questions like, hey, I just saw an outcome of a match of tug of war. How strong is that player? How strong is this other player? So to keep it short, we can write down a little web people program that captures the concepts for reasoning about tug of war as functions in the programming language, stochastic functions. So strength is a function that takes a person and returns a real number, which is their strength. This mem means memoize it because a person's strength doesn't change from match to match, so keep it consistent. Laziness is a function from a person to whether or not they're lazy. That does change from match to match. We care about how hard somebody's pulling, and I'm going to arbitrarily kind of make the simplest assumption, which is that the amount that a person is pulling depends on whether they're lazy. If they're lazy, they pull with half their strength, and if they're not, they pull with their whole strength. By the way, when I first wrote this down years and years ago, this was just like literally the simplest program that I could think to write to capture this set of concepts. Sometimes being naive actually is very useful. Total pulling, okay, there are teams in tug of war, so we actually care about how much strength the entire team is exerting. No problem, that's just a linear sum of how strong each person, how much pulling each person is doing. So map the pulling function across the team, take the sum of those amounts of pulling. And finally, we only care because we care about which team beat which other team. So beat is a function that takes two teams and checks whether the total pulling of team 1 is greater than the total pulling of team 2. And if so, then team 1 beat team 2. Okay. Oh yeah, I had this note down here because I wanted to make sure to tell you. So we made this as a thought experiment, a kind of cognitive science meets AI thought experiment a bunch of years ago, maybe 6 or 8 years ago. We then discovered sometime later that Microsoft had independently created this, and they called it the TrueSkill trademark algorithm that they used in Xbox for a long time for matching up players so that they would have fun games and they wouldn't just always lose terribly. Okay, so when we want to use this kind of knowledge in order to do an uncertain inference, we just use that infer function, and we say something like, let's imagine that we saw Bob and Mary beat Tom and Sue, and Bob and Bev beat Jane and Jim. I want to know how strong Bob is, right? Very straightforward. One important thing is, notice that I never mentioned what the matches were or who the players were when I was declaring the knowledge, and that means I can use the same sort of pieces of components in lots of different ways. That's the sense in which this kind of probabilistic program representation captures a really interesting amount of abstraction. Okay, so because I'm not just an AI guy, I'm also a psychologist, I went and did this experiment. I said, what would people say when you gave them that kind of evidence and asked them how strong Bob was? So my colleague Toby Gerstenberg and I went to Mechanical Turk, and we showed players a bunch of tournaments where there was a bunch of matches in the outcome. We did singles and doubles tournaments. And in each case, we just chose one of the players and said, hey, how strong is player IE there? And here's the results compared to the model predictions. So on the horizontal axis, this is the average strength judged by the humans for each condition. Each dot is a condition. And on the vertical axis is the model predicted strength, the expected strength according to the model. You'll notice that there's a very nice line here, and that's the important thing, because that means that the model is predicting all of the variance in the human judgments, right? People have actually pretty complicated judgments that depend on the patterns of data, and this model is able to predict it. So even though I wrote down kind of the most naive model, it was sufficiently structured and abstract to capture what people seem to be doing when they're reasoning about the strength of players in these team games. Also what Microsoft decided players were doing. Okay, that was first example. Now, so far, what I've shown you is something that has some elements of abstraction and some elements of uncertainty, but nothing social. And I promised you social, right? So here's an interesting game. This is a kind of game called a reference game, initially described by the philosopher David Lewis, like maybe 60 years ago. There's two players in this game. There's the speaker. So if you're the speaker, you should imagine that you're talking to somebody and you have to convey the middle object here, and you're only allowed to use the word blue or the word circle. Okay, how many of you are going to say blue? How many are going to say circle? Okay, except for one smart aleck, everybody says circle here. That's good. This is the warm-up. There's another player in this game, the listener. And it's just the other side. So imagine if you're the listener that somebody uses the word blue, and you have to figure out which object they're referring to. How many people think it's the middle one? One or two. And how many think it's this one? Most of the rest, but not entirely confident. I'll show you the results of these experiments in a minute. What usually happens here is that people look at this and they say, well, if I was trying to talk about this object, I could say circle. So if I said blue, I'm probably trying to talk about this one where there's no really good way to talk about it, right? Interestingly, that requires thinking about how the other person is thinking about the particular reference, right? Well, I would have, if he was going to say this, he could have, sorry, if he had meant that, he could have said this, that kind of reasoning. So this is really fun because it's a very social example where if you don't do the social reasoning, the kind of recursive social, I think that you think that I think, you can't do anything interesting in this setting, even though it's a super simple game. Okay, so here's how we capture that recursive social reasoning with a probabilistic program. First, there's a literal listener that doesn't do anything social. This literal listener simply says, okay, I'm going to do an inference, which is to figure out what is the target object, assuming that the object actually has the property that I heard. So if they say blue, it's got to be one of the blue ones, but otherwise I don't know. Right? So that listener doesn't strengthen the meaning. It could mean either the blue square or the blue circle. So then we go on and we say, what about modeling a speaker who is thinking about that listener? So here's a speaker that says, I'm going to do an inference. I'm interested in what property I should say. And I'm going to assume that if the literal listener hears the property and makes a guess, they're going to guess the correct object. Right? So another way of paraphrasing this model is, what should I say such that the literal listener will make the right guess? So it's because this stochastic function calls this other stochastic function that this becomes basically a social model, right? It's one inference thinking about another inference. We can go a little bit farther now and we can say, okay, then there's a fancy listener. The fancy listener is doing an inference which is the same. They're figuring out what the target object is. But here, under the assumption that if the speaker had been trying to convey that object, they would have said the utterance that the listener actually heard. So this is sometimes called a pragmatic listener. Pragmatics is this kind of context sensitivity of language. Okay, here's what's interesting about this model. There are basically no free parameters that I have to specify, except that, I have to tell you where this reference prior comes from. This says, how likely is somebody to refer to a given object a priori? So we're going to measure that empirically. If you're interested in this kind of thing, I'm just going to give you the kind of tip of the iceberg of this story. This basic approach has been extended by myself and colleagues in an approach to language understanding called the Rational Speech Act theory. And it does all sorts of really cool things. It can capture hyperbole and metaphor and a lot of these kind of interesting figurative aspects of language. That's a different talk. Happy to show it to you guys some other time. But okay, so we went and we decided to test this very simple reference game model. We did the game exactly the way that I did it with you guys, but with subjects online on Mechanical Turk. We systematically varied what the three objects were. There were two binary features, and we did all combinations of two binary features. And we had three conditions. We had the speaker. By the way, you're not supposed to be able to read the text. It's very, very small. We had the speaker, and the speaker was just, you have to refer to one of these objects. What are you going to say? We had the listener. The speaker says dotted, which one do you think it is? And then we had what I'm calling the prior condition. Here we said, the speaker, somebody is talking to you and uses a word you don't catch. Which object do you think they're talking about? So this gives us the prior over what people are likely to be talking about. And so what we do now is we take the results from this prior condition and we plug it into the model, and that fully specifies predictions for the other two conditions, listener and speaker, right? And the results are pretty awesome. So this model, again, I'm showing you model predictions on in this case, the horizontal axis, and human behavioral judgments on the vertical axis. And the correlation here is about 98%, or correlation is about 0.99. So even though people do actually do very nuanced things in this situation, the model is able to capture those nuances by doing this recursive social reasoning. Okay. Here is a, oh, I'm going to get through 3. Cool. Here is a little interim recap of this. So far, I want you to interpret it, what I've shown you as this. We get from programming languages the correct means of abstraction. We know how to make units of knowledge that are abstract enough to be used in lots of different places. From probabilities and probabilistic inference, we get coherent reasoning under uncertainty that lets us deal with lack of knowledge and noise and make predictions that are consistent with the judgments that humans make. Using those two pieces together, we can write down these structured models that have an inference about an inference about an inference, and that captures aspects of social cognition. So I could declare victory now. This is what I promised you I was going to be thinking about here. But there's probably a kind of nagging property, since everybody knows that, well, as of this year, maybe not 3 years ago, everybody knows that the key thing for artificial intelligence is machine learning, with the learning in there. You might be wondering, what about learning? Okay, so I don't have time to get into a whole lot of details here, but I want to just kind of mention an interesting direction that I think is going to be super important in the coming years, which is a merger between deep learning techniques and probabilistic programming languages. Again, you're not supposed to be able to read through all of this, but I'm going to tell you what you're looking at. We've done a little bit of work in this direction. The basic idea is that you can think of taking your probabilistic program and then annotating it with additional knowledge, which is not knowledge about the world. It's not knowledge about how to generate the data. Instead, it's knowledge about how to do inference. So you can think of this as adding knowledge, which is knowledge that you're going to learn about how you do inference in a particular model. So that's why in this little diagram, what I've written here is basically a very simple Gaussian mixture model. The details aren't important. And critically, we add these dotted arrows that tell you how to go not just from whatever is latent that we're interested in to the data, but how to go backwards from the data to the latent stuff. The key trick here is that we use all the power of modern neural nets, so big, fancy multi-layer perceptrons with gradient learning, in order to learn the knowledge about how to do inference, potentially solving one of the real drawbacks of probabilistic programs, which is that inference is hard. Universal inference is hard. But if you learn how to do inference, maybe it gets easier. I can't tell you the details there, but what I can do is show you a pretty example. So my grad student Daniel Ritchie and I started by writing down a little procedural graphics probabilistic program that describes these vine pictures, and then posing as a probabilistic program the inference, which you could say is infer a vine that looks like this target shape. Okay. That's nice because it's very hard to explicitly write a program that will generate a vine that looks like a heart in this case, but it's very easy to write it as an inference. You basically say, write the program that generates crazy vines, the prior, and then add the condition which says the difference between what you generate and the mask is not very big. So what we want is to get output like that. And the basic idea here is that we could get results like that very, 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 very slowly by using what's called a particle filter, but it's not fast enough to be useful. So instead, we're going to add this crazy neural net, obligatory crazy neural net picture here, that starts with the mask and what you've generated so far, and does a bunch of stuff to predict what choice should I make next as I run my program. And then we're going to train this crazy neural net from the model itself to learn how to do these inferences faster and faster. Here is a picture of the results. The top is what we get when we use our system to generate letters that obviously are intended to look like SIGGRAPH. The next one is what you get from an equal number of computation steps, and the bottom one is what you get from an equal amount of time without using the trained system. So clearly, this system is learning how to do inference in a really useful way. And I'm going to close by showing you a cool movie of this system running. On the left is going to be our system, and on the right is the comparison that doesn't do any learning about how to do inference. I'll let you stare at this while it goes because it's quite edifying. And I will thank you for listening. and I'm happy to take questions.